Hello everyone, this is Cherry, Ling Chen from CSIRO Manufacturing Australia. Today I'm going to give a presentation on the characterization of reversibly-actuating shape memory alloy foils produced by Planar forecasting. Shape memory alloy is a smart material. It remembers its shape. After deformation, it can recover its original shape under thermal stimulants. So here's some example of these alloys like copper, aluminium, nickel, copper, zinc, aluminium, and nickel, titanium alloys. So this is the figure showing the mechanism of the shape memory alloys transformation, the shape. Basically, it has three different phases. So it's the transformation between these phases. For example, when the material at the molten side phase and it has been loaded and it can be bended. And when the temperature increase higher than the austenite transformation temperature, the shape will change, recover to its original shape and is in the austenite phase. So normally there are two types of shape memory effect. One is the one-way shape memory effect. That means after the material deform and the temperature heat up to higher than the austenite transformation temperature, and it will come back to the original shape. And when the temperature cool down again, the shape just remains the same as the original one. But for the two-way shape memory effect, when the temperature cool down, it can have a second shape, which is different from the shape heated up at the austenite phase, and also different from the original shape. And this is what we normally need for many applications, especially for the sensor and actuation. So here we use a planar flow casting measure to fabricate shape memory alloy foil. So there are many advantages of this measure, such as low cost, and it can be used in mass production. And it is a rapid solidification process. It can form metastable phases, which can facilitate shape memory effect. And the thin film can be used in a very small and tiny sensor than the actuator. Here is the schematic of the planar forecasting process. Here we can see this is a crucible, and we can put the nickel and the titanium in, and it can be melted by the arc melting. And this liquid metal can come out from the nozzle and then hit the quenching wheel, which is rotating. And this can be spinned out into the nickel titanium foil. So here is the contact area, like this area. Then we can see if there are many parameters we can adjust to get a appropriate or nice foil we want, such as the width of this nozzle gap and also the gap between the nozzle and the quenching wheel and rotation speed of the quenching wheel. And this is the photo showing the planar forecast nickel titanium foil produced by us. And after we have the material, we need to do the heat treatment and also the training to set the original shape and achieve this two-way shape memory effect. So we made these kinds of V-shaped steel mold, and the material can easily insert and then keep the shape here. And then we put this mold with the material into the furnace and at 3 different temperature under 30 minutes and under argon. And after that, we quench in the water. And after we take it out, we can see the foil has been set the shape as the V, and we cut a slope in between. So we use different thermal or annealing temperature to see how this temperature can affect the shape memory behavior. And also for the training process, we connect these two ends of this material with the current and flatten this foil. And with the current on, it will recover back to its V shape, and when the current off, and it will form a second shape which has a slightly bigger angle than the one with current on. And then we can repeat this step, flatten the foil and the current and current off as the second cycle. So we did 30 cycles for the material to see if the training cycle have any effect on the shape memory behavior. So we did the thermal analysis methods like DSC to check the phase transformation temperature of the planar force coupling material and also a commercial material as a comparison. So we can see that we have the Martensite start and finish and the austenite start and finish temperature. And we find that when the annealing temperature increase, the transformation temperature actually is reduced for the planar forecasting material. But for the commercial one, it behavior differently. Here we can say that the transformation temperature can be addressed by the heat treatment or annealing temperature. And also it can be found with different material using different fabrication method. So in this study, we fixed to 550 for the whole study. And this slide tells us the effect of training cycle on the shape memory effect. And we can know that here is the planar forecast material and this is the commercial one. And we have the material with current on and the current off. And we can see the angles different between these two states. And for the planar forecast material, without any training cycle, it can have 30-degree difference between these two angles. But for the commercial one, there is nothing change when the current on or off. So, and then after the first cycle, we can see the angle difference is 20 degrees for the planar forecasting material, but for the commercial one, it's only 15 degrees. And we can see the angles keep increasing, both for the planar cast material and the commercial one. But after 30 cycles, the angle difference increased to 55 degrees for the planar forecast material, but for the commercial ones, it's only 32 degrees. So this study shows us the planar forecast material fabrication. This study can show a two-way shape memory effect without training. And it also shows a larger deformation compared to the commercial one. We also set up a measurement procedure for measure the force generation during the actuation and the recovery. So we use the two clamp to fix or constrain the material, and when the current on, it try to recover back into the V shape, but it has been constrained. So the force generated during the shape changing can be recorded by the load cell. And here is the two plot showing the stress and temperature versus temperature. And we can see that both the planar forecast material and the commercial one, they have two peaks in the stress. One is when the temperature increase and the other one's during the temperatures come down. And we can see that for the planar forecast material, it have much higher stress, whatever at the actuation point or at the recovering stage, and also have a much shorter actuation time and the recovery time compared to the commercial one. And in this study, we also developed a machine learning workflow for shape memory effect characterization. Basically, we use the experimental thermal video as the data, and then develop an automatic video analyzer. And it can extract the key feature points of the video and also some thermal hotspot. And it can be used to derive this model. And the model can be trained and predict the shape memory performance in terms of the shape, and also the angle change, and also the force generation. So here is the video after the process. Then we can see this is temperature increased and is the angle become bigger, and we can tell from the center of this material and what's the angle changing, and also the force prediction is showing here. So it's a comparison study between the Planar forecast material and the commercial ones was carried out. Here's a small summary. And the phase transformation temperature of nickel titanium shape memory alloy is adjustable. And this material show a reversible actuation before any training cycle. And the material can show a larger actuation degree compared to the commercial one. And this material outperformed the commercial ones in terms of larger stress and the generation faster response time. And it will offer more opportunity for the practical use as micro actuator or sensor with higher sensitivity in a more controllable way. And this machine learning based model is developed for force and shape prediction, which will be very handy for the practical use for the material design. So this is the end of my presentation. Thank you very much for your listening.